Okay, hi, this is a recording of the multiple choice from test 1 for our differential equations class. If we scroll down, only going to go through the multiple choice here, and I'll make another video for the other problems and the other multiple choice, maybe. Which of the following are not, no, which of the following are first order nonlinear differential equations? Mark all that apply, and we want nonlinear. So first order, that's where the highest derivative present on the dependent variable is 1. So that's out because of y double prime. So this is first order, this is first order, this is first order. Nonlinear, what does that mean? It means the coefficients on the dependent pieces, like y prime and y, the coefficients have to be linear, they need to be constant, or they need to be expressions depending at most on t. So this one is linear. This one is non-linear because the coefficient on the y prime is a non-constant and it's y. It depends on the dependent variable. It's not depending on t, and it's not depending as a constant. So this one, we'll select, choose blue. That's nonlinear. Linear. Nonlinear. This one also linear. Linear again, because if you look at the dependent pieces, the y prime, the y here, the coefficients on those terms are either constant like the 3, constant like the 1, or expressions of t like e to the t. All right, number 2, the implicit solution to the initial value problem given, okay, find the c. So we need to plug in, let's choose blue. When x is, so y is dependent, x then is 2 is independent. Let's plug in a 2 for x. So 2 there and a 2 there, and then set it equal to -4, find c. So let's see, plugging in a 2. So 2 squared y squared plus y over 2 is equal to 3 times 2 plus c, and y is a -4. We know that when we plug in a 2 for x, y becomes a -4. So we can plug in a -4 for our y's. And what do we get there? So that's 4 times 16, that's 64 minus 2 is equal to 6 plus c. And if we move the 6 over, that's 64 minus 8. 656 is c. Let's keep going. Which of the following initial values are guaranteed to have a unique solution by the existence uniqueness theorem from first order? Let's see. So let's go one by one. We're really wondering for each of these, look at the input values 0, 1, 3, and 0. And as we look at these problems, the right-hand side, so the left-hand side of each problem is a y prime, a y prime, a y prime. The bottom one would be y prime is -4ty plus e to the -t. And the first condition is that these right-hand sides all need to be defined when you plug in an input of 0, 1, 3, or 0. So an input is t. So t being 0 right there is fine. T being 1 right here, that'd be sine of y, that's fine. T being 1 here is fine. T being 1 here or here is fine and continuous. Then if we look at y being 1, y being 0, 0, and 3, also at those right-hand sides. It's okay for y to be 1 there. It's okay for y to be 0 here. You'd have sine of 0, that's defined. If we plug in a 0 there, root 0, also okay. If we plug in a 3 there, we're okay. So the first condition is met. The second condition, you need to look at the partial derivatives of the right-hand sides with respect to the dependent variable. If we do that, let's see, the partial of y prime with respect to y is negative t over y squared. Again, in this expression, it's fine for t to be 0 and y to be 1 defined. So this is defined at 0, 1. So which of the following are guaranteed? So that's one. The others, let's see, your partial derivative of sine of ty, that's going to be cosine. So partial y prime with respect to y is going to be cosine ty times the derivative of the inner function, that's going to be t. This is also, let's see, defined when t is 3 and y is 0, cosine 0 is 1. That's fine, and that works. So that one. If we look at the last one, if we look at our partial derivative, we have negative 4t. This goes to 0. So if we're just looking at, just looking at negative 4t, just looking at negative 4t, totally fine for t to be 0. So this last one works. Then the middle one, though, or the third one, if we take a partial derivative of t root y, we would have partial derivative y prime of, with respect to y, t root y, that's a t, and 1 over 2 root y for the derivative of root y. And look, so we're plugging in t being 3, that's okay right there. Y being 0 can't happen in a denominator, so we're not guaranteed to have a unique solution by the theorem for that third piece. Next one, let y prime equal that thing, y cubed minus 1. Which of the following statements are true? Mark all that apply. So our equilibrium solutions, if we set y prime, y cubed minus 1, that's when y is 0 and y is a plus or minus 1. No, let's see, negative 1 would be, no, just plus 1. Plus 1. So if we look at a phase line, we have 0, we have 1. We need to know what's happening to answer questions like the equilibrium solution 0 and 1 being semi-stable or stable. We need to know what the derivative is doing. Is it positive or negative around these values? So let's think through that. If we pick, say, y being 2, y is 2, will the derivative be positive or negative? So positive 2 there, then we'd have 8 minus 1, that's going to be positive. So our derivative is positive on that interval. Then between 0 and 1, say 1/2. 1/2 there would be an 1/8 minus 1, that's negative. A half here is positive, so negative on that interval. And below 0, say -1. -1 would be negative here. And -1 minus 1 is a negative as well. The two negatives make a positive. So derivative is positive there. Then that makes 1, y equals 1, what, unstable? Y equals 0, stable. And then the others, let's see, which of the following are true. So I'm going to pause just a sec. Yeah, we're back. So y of t, the zero, that equilibrium solution there is stable. That's true. Y1 being semi-stable, that's false because it's unstable. So we're not going to select that one. That one's out. And let's see, if we had an initial condition, y of 0 is a half. So if we look at 1/2, say in here, 1/2, what's going to happen as time increases? So let's look at a solution. If we were going through y being a half, then what's a solution going to do? It's going to come through like this and level out. As we approach 0, it's not going to go to 1. So this, not true. If we go through 2, let's use blue. If we go through 2 up here, then the graph is going to increase without bound. It's going to go to infinity. So this is also not true, just the top one. Which technique can be used to solve differential equation? Mark all that apply. Let's see. So your first step is maybe to think through this differential equation. Y prime minus ty is equal to y to the -1. And decide if it's linear or nonlinear. This piece here makes it nonlinear. Again, because to be linear, your y dependent pieces, the y prime, this y, and this y all have to appear linearly to the power 1, and this one is not. So nonlinear as nonlinear differential equation, we automatically know integrating factor is out. We automatically know method of undetermined coefficients is out. Then if it's separable, we could use separation. And as long as, let's see, in this form, we have y prime minus the some coefficient of the dependent variable, y, equals, so y prime minus t, y is equal to y. As long as this isn't 0 or 1, then we could use the Bernoulli method. So Bernoulli works. Again, because our exponent fits the form and the whole equation fits the form for our Bernoulli substitution. And then separation of variables, could you factor the right-hand side such that, so we have y prime equals the right-hand side is ty plus 1 over y. Can you factor out a y or a t so that you change the right side into a factorization of terms where it's independent things times dependent things, not a mix? And if you did, let's say you took out a y, then you'd have t plus 1 over y squared. Would that work? If you put the y back in, you'd have yt, you'd have y over y squared, that'd be 1 over y. So you factored, but you have a dependent thing, and then this other factor still has independent and dependent, so not separable, just the Bernoulli transformation. Next one, make the leading coefficient 1 by dividing by 4, you'd have y prime plus 3/4 y is equal to t squared. This is linear. As it is linear, Bernoulli's out. Method of undetermined coefficient, well, integrating factor you can use straight away because it's linear. You can use undetermined coefficients if the coefficients on the dependent pieces are constants, and they are. You have a 1, you have a 3/4. 1 there, you have a 3/4 there that are constant. You can use undetermined coefficients. Then separation of variables only if it's separable. It is not separable. Again, if you take the y prime equals t squared minus 3/4 y, there's no way you're going to factor this right-hand side into y things and t things. Which of the following is the correct form? For the general solution, let's put leading coefficient 1, so y prime plus 6/2y is equal to 3/2 cosine 2t. Okay, so a couple things. The 3/2 cosine 2t in particular solution form, the right-hand side, the particular piece, the y sub p, is going to have an a cosine 2t and a b sine 2t. So the top equation, this is not an option. This is not an option. And the difference between these other two is the e to the negative 6t, e to the negative 3t. When you solve the y prime plus 3y, you would get, as a homogeneous solution, let's see, for y sub h, we would get y prime equals negative 3y. This tells us that y is some c e to the negative 3t. So we're going to pick that one. The rabbit modeling problem, modeling rabbit populations are t's number of rabbits in the backyard at time t in weeks. K is a constant. Rabbits grow at a rate proportional to the rabbit population. That gives us K times an R. So this last one is out. Then each week the rabbits 10 escape. So each week you lose 10. So the loss of 10 is not dependent on anything besides a week. It's not growing proportional, anything like that. So we're going to pick this one. The other options, like we already said, that was out. This equation here incorporates the minus 10 with the growth constant. Not going to work. The top one incorporates negative 10 times the current rabbit population. That's also not happening. So number 9 equation can be changed with the Bernoulli transformation. What do you get after you change? So we'd have y prime plus 3/ty is equal to e to the t over t y to the negative 3 for the, and you do that because you got to divide by t to make the leading coefficient 1. Y to the, so mu, is it mu? I think we use, no, I think we use u is y to the 1 minus n. So that's y to the 1 minus a negative 3. Here is your n value. So it's going to be y plus 3. That's y to the 4. Then we take derivative of u by t, and that's going to be 4y cubed dy dt. Then we multiply this piece, 4y cubed, to the entire equation. And when we do that, so 4y cubed we get 4y cubed y prime plus 12/t y to the 4 is equal to e to the t, 4e to the t over t, and the y cubed there cancels that one. Then what happens? So the 4y cubed y prime, that's this. So that's going to be substituted for a du dt. So all of this becomes du dt, or u prime, plus 12/t. Now y to the 4, that's what u was. So u equals 4e to the t over t. So top one. I think we have 2 more. Let's see, enthusiasm, E of t, differential equation growing, semester progresses, model the equation, okay, that. initial enthusiasm is this, you got an initial condition, and then 5 weeks later, you have another condition, find the rate constant. All right, so we have E prime is equal to KE. That tells us the solution is going to be AE to the KT. That's one you need to know for exponential growth. If you don't know it, you could solve this with separation. You could solve it with integrating factor. You could solve it with muck, but you don't want to do those. You just want to know that this is the solution for exponential growth. Then we know that, let's see, E of 0 is 10. We know that's going to be our A value, but just to show you, E of 0 is A e to the K times 0, and that's 10. So A times e to the 0, that's 1. A is 10. So if we update our model, we have 10 e to the kt. Now we want to plug in 5 for t and set it all equal to 100. So you have 5, 10 e to the 5k is equal to 100. We're solving for k. If you divide by 10, then what? Natural log both sides. Then you'd have 5k. Natural log of e is natural log of 10. Natural log of e is 1. Divide by 5. K is natural log 10. Divide by 5. So that's this one. Okay, last one, matching of the pictures. So notice that each of these pictures has an equilibrium solution at 120, 120, 120, 120. And all of these solutions, all these differential equations show that if you were to plug in 100, plug in 20, it would set the equation to 0. So what changes is the flow away from these equilibrium solutions. So pick some values. Let's pick, let's look at 120. And if we plug in 120 to these equations, what are our signs? This 120 here, 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 and here, we would get negative, negative, positive, positive. If we plug in 120 here, there, 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 then it's going to be 120 over 100 is bigger than 1, so it's going to be negative across the board. We'd get a negative, 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 negative. 120 here, also going to be bigger than 20, so this value is going to be bigger than 1. It's going to be negative. Negative, 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 negative. And what's our overall sign? We'd have 3 negatives, so this gives us a negative derivative. This gives us a negative derivative, positive derivative, positive derivative. So let's see. We picked 120. In the top equation, A, we have a negative derivative. So the flow should be decaying towards 100, or the flow shouldn't be going up, it should be going down. And so this one would work for A. This one would work for A. So maybe A there, maybe A there. Then what else? I guess these could be B. This could be B, since again, we had negatives in our derivatives when we plugged in 120. So this other graph, this is either C or D. and this one is C or D to be positive at 120. So positive at 120, positive at 120. Then we need to look for a value between 20 and 100 or below 20. I don't know, let's do below about 40. We pick 40. Gonna go back, well, let's see, this was at y is 120. We pick at y being 40, then again, these first values are negative, negative, plus, plus, negative, negative, plus, plus. The next values, if we pick 40, 40 over 100 is less than 1. So these are all going to be positive. 40 over 20 is bigger than 1. These are all going to be negative. So plus, 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 negative, 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 negative. And overall, then we get positive, positive, negative, negative. That tells us at 40, the graphs should be, let's see, these top two should be increasing between or at 40 like this. And the other two, I shouldn't have picked 40, decreasing and decreasing, and they do. We should have picked, looking at this picture and this picture, they're both have an increasing trajectory between 20 and 40. So we should have picked this and this one. Oh, and then these, that goes and that goes, they both go plus. So we didn't need this. Didn't need that. How are we going to decide which graph matches which? Okay, so what do you think? I think you need to look at these first factors. Let's look at C and D. So if you plug in a value for Y, you have, think of 0.06 as a, I don't know, kind of like a slope, 0.16 as a slope. 0.16 is greater than 0.06. So if you look at, say, what are we looking at, C and D? What's steeper? Like if you look, say, in this section, that is steeper than this line here. So this would grow at a slower rate, like the 0.06 there, and this would grow at a faster rate, like the 0.16 there. So C matches 2, and C matches 2, and D matches 3. C matches 2, D matches 3. Then let's look at the other. Again, 0.16 is going to give you a steeper graph than 0.06. Let's look, I don't know, between here and here. This is steeper than these. So this correlates with B, this correlates with A. So A is 1, B is 4, and I think that's it. Next up would be number 12, and we'll do that another day. Y'all take care.